MacMaths, let's do some maths today. Hello, welcome back. So this is lesson 2 of my AS Mechanics. I'm looking at chapter 9, the start of chapter 9. For Pearson, AS Maths it starts off looking at distance time graphs and velocity time graphs. So I'm going to look at the two today. This is going to cover exercises 9A and 9B. But I'm going to go through the two different types of graph with you. I'm not going to spend too long on the distance time graph, and I'll just zoom in on this one. So this is exercise 9A. You'll recognise this from GCSE, and they're very simple and straightforward. They don't really tell you a lot. It's based on, say, a real life situation of someone perhaps walking to the park and then walking home again. And this here, this distance, or better to think of it as displacement, is the distance they are away from home at any time. So they start off here at home, so they're no kilometres away from home. I've not used SI units, I've only used kilometres, and the time is in hours. So they start at home and they start walking at a steady speed, and after 3 hours they reach, I put dotted yellow lines in, they've reached 12 kilometres away from their starting position. You're often at GCSE asked to describe these, so you could describe at foundation level a person walking for 3 hours and reaching it's a straight line, so it's a constant velocity or speed, and reaching somewhere 12 kilometres away from home. At that point it may be the park. They stay in the park for an hour. So for this hour they are not any closer or any further away from home, from our zero line. So they spend an hour in the park, and then of course they walk back at another constant velocity. You can go at higher tier at GCSE, you can go a step further, you can work out this velocity. And this is where this comes into place, doesn't it? That you know that if you've got a speed times a time, they use S for speed. Speed times time is equal to distance. So if you're travelling at 3 meters per second for 4 seconds, you're going 3 times 4 is 12. You travel for 12 meters. And we can apply that to here. You can see that if you rearrange that, then that the speed is equal to the distance divided by time, just dividing both sides by time. And that's what we do here. You know that from GCSE. The distance is 12, okay, and you do that over 3 seconds. So if you do 12 divided by 3, it gives you 4, would be meters per second, but in this it's kilometers per hour. So this is a person in this section here that is travelling at 4 kilometers per hour for 3 hours, and in that time then obviously they'll reach 12 kilometers. They do nothing for an hour. They just sit in the park, so they don't travel any further away. So this is a zero velocity. And then they walk back, and again they walk back 12 kilometers over 4, so 12 divided by 4 this time is 3 kilometers per hour, but it's 3 kilometers in the opposite direction. It's a negative velocity, so it's going back the other way. Okay, and that's this section here, and they've travelled 12 kilometers, and that's, you know, GCSE level. And those ones describing those little journeys like that are in the book in exercise 9A. But there's more interest for us really in the velocity time graph. They can do a little bit more. And I want to look at this side then. Actually, this side, you don't often see them drawn like this, but this side shows this same journey. You can see here that we worked out the velocity. This is a velocity time graph. So along the side, so this is the S here, the speed. And and this is the time. It gets a little bit confusing because actually in mechanics we use S for displacement, the distance away from a particular place. That's the letter that we're going to use in the formulas, and we don't use the letter D for distance. So let's compare this side to this side. So we know that we were travelling for 4 kilometres per hour for 3 hours. Well, there it is. This is the time. For 3 hours, you're travelling at 4 kilometres per hour. So this is a constant velocity of 4 kilometres per hour for 3 hours. Then, for 1 hour, between 3 and 4, the velocity suddenly drops to 0. So you're not travelling at all, you're stationary. And then we're travelling at 3 kilometres per hour for 4 hours. Okay, we work that out. Now here, velocity is speed with direction, and the direction is the other way. In other words, the velocity is now -3, and it just means that instead of being that way, the velocity is in the opposite direction. Okay, so that's why this is drawn underneath here. And this allows me to show you another feature, or a good feature of velocity time graphs, because you can see here that from this statement that the speed, I'm just going to change that to a V now, the velocity times time is the distance, and this is the velocity, that side of our rectangle, and this is the time. And you can see that velocity times time, we know, gives us 12, the 12 kilometres away from home. And this is a feature of velocity time graphs, and that feature is that the area is equal to the distance travelled. I'm going to call that displacement. Oops, and the T's going on my board. So the area here of these is the displacement, and we can work that out by going the area under the graph, really, which, because this is a rectangle, as you know, is just velocity times time, so length times width, which is the 12. Okay, this one is also 3 times 4, which is also 12. So all in all, this person is travelling 12 kilometres in one direction, and this is a -12 because it's below the graph, 12 kilometres back home. So these two are the same journey described using distance time and velocity time. But now we're going to move on to velocity time graphs. And our velocity time graphs don't, I'm just going to zoom out again now. I can just zoom out, there we go. Our velocity time graphs don't often look like that, because we can show another feature on velocity time graphs. And I'll show you one of those features, if I can find it. I did have it a second ago, but no, I've now lost it. There it is. Okay, so this is a typical velocity time graph. I'll just again zoom in on that. There we go. You can see here now that we've got not a straight line like in the last one, we've got a sloping line. And actually this means that the velocity is changing, and the velocity is changing with time. And from this we can actually, this slope, of course, a change of velocity with time is acceleration. So this is someone who starts at home and speeds up to a velocity of 8 meters per second, travels at 8 meters per second at constant velocity for between 4 and 10 seconds. So for 6 seconds, let's draw the dotted lines down. Okay, and then slows down, so from this point of 8 meters per second, slows down to 0 meters per second over 8 seconds. So this is a journey that a particle or a person or a car is taking it's done actually now in SI units, in meters per second. And we can work out the acceleration and the deceleration by doing the velocity. It's the gradient of the line actually, so it's y over x, it's velocity divided by time. So velocity divided by time, so 8 divided by 4 is 2 meters per second to the minus 2. Okay, so in this region the car or person is accelerating at 2 meters per second until it reaches this is acceleration, this is a period of acceleration, this is constant velocity at 8 meters per second, isn't it, that part there, and that is for 6 seconds, you can see, and then it continues on, and it decelerates. So this is 8, that distance, divided by 8. Okay, so that is velocity divided by time, is 1 meters per second squared. So it decelerates at 1 meters per second. We can put that in, you can see that's a negative slope, so the minus just means that it's decelerating, really it's a negative slope, but you can either put it in as minus 1 meters per second squared, but we like to say use the actual word of acceleration and deceleration of 1 meters per second squared. That's what's happening. But a nice feature of this, of course, is that if I zoom out now, a nice feature of this, of course, is although it's not a rectangle, it is a parallelogram, and the area under this parallelogram, hang on a minute, I'm talking about a parallelogram, it is a trapezium, sorry, I do know my shapes, I did learn them. This trapezium, the area underneath this trapezium, just like the, where have I found it, oh, there it is, just like this one, is the area is the displacement, or the distance travelled. So this is a journey in one direction, you know, like the pop group. Okay, so it's a journey that's 18 seconds long, car speeds up, travels at a constant velocity and then slows down, and the area underneath this graph is the total distance travelled. This is where it's good to, rather than, you can see it's a triangle, a rectangle and a triangle, and you can just do base times height divided by 2, length times width and so on, but it's good really here to remember your formula for your trapezium, not parallelogram, and your formula for your trapezium is this formula, isn't it? Where you've got, there's your trapezium, your A and your B are your two parallel sides, and that is your height, is your distance between them. And the formula is a half of, you add your A and B, halve them, and times by the distance between them. So for this one here, the area would be a half times, well, we've got 6 plus 18, and we're going to times that by the height there, which is 8. So applying this formula to this shape, this trapezium, 6 add 18 is 24, halved is 12, so we're going to do 12 times 8, the height of our trapezium, and 12 times 8 is 96. That means that this, in this particular journey, speeding up by 2 meters per second, accelerating for 2 meters per second for 4 seconds, constant velocity of 8 meters per second for 6 seconds, and then decelerating at 1 meters, decelerating at 1 meters per second squared for the remaining 8 seconds, means that this person would travel 96 meters. Okay, so that's the main feature, that is what you're going to be doing. I'm going to give you a few bewares. They may look like this. What's happening here? What's happening here? Well, let me just rub that out just in case you just fast forwarded through and you thought that applied to this. It doesn't. We've got two trapeziums here, one above and one below, and of course what's happening here is this is my start and this is some point. I don't know, I'm going to write point there, I don't know why. Okay, and what's happening here with this one is that it's speeding up, constant velocity, decelerating to 0 and stopping at this point, velocity is 0, and this now is an acceleration increasing speed to -3 meters per second. Now the fact it's minus, what's happening is he's speeded up, gone all the way, slowed down, stopped there, immediately hit the reverse in the car or started walking back, and is speeding up, going in the opposite direction, constant velocity back, and then decelerating a little bit and stopping again. So they're actually, you know, doing that. That's what that journey is. The minus is coming back the other way. You do have to be careful about what you think about acceleration and deceleration in this region here, because it's accelerating and decelerating in the opposite direction. So you've got to think about it practically. But you can see that the total distance travelled is the areas of these two, not a negative area, it's just coming back the other way. But if you take that away from that, it tells you the displacement, the distance you are from home, doesn't it? Okay, so this is just a two-directional thing. It's going in one direction and it's coming back. Okay, this is the amount it comes back, the negative area. Okay, so you may get ones like that. And finally, and I don't think it's, I've not zoomed, yeah, I've zoomed out. So I've got two for you here. Okay, so these are more likely what you're going to see in the questions. You're often asked to sketch, you're given a situation and you're asked to sketch a velocity time graph. So just put the key points on. I always do the dotted lines, a period of acceleration, a period of constant velocity, and a period of deceleration. You can see that this whole journey took 110 seconds and they reached a speed of 10 meters per second. This is a trapezium, so we can just do the maths on that. This one here, they don't, I just drew this one finally for you before I end the lesson. They don't have to start at 0, do they? They can say that a train passes a point travelling at 6 meters per second and accelerating. So sometimes they start, you know, from a point up the velocity axis from a fixed velocity. So this particular one, if you were doing this one and you wanted to find out how far it's travelled, you've just got to adjust the maths that you do. This is not a trapezium anymore, but this part of it, if we split it up now, this first part of it, I'll call it I'm going to call it two sections actually. I could split it up into three sections, A, B and C, but I'm going to do A is this first section here, and you can see that this first section here is a trapezium on its side, this lean-to shed shape. You saw those at GCSE, and this velocity here, it starts at 6, so this distance here is 6, and this side here is 10, and it's 30 along the bottom. So the area of this one is a half of A plus B times H, so it would be a half of, wouldn't it? Those are your two parallel sides, 6 add 10, times the distance between them, which is 30. 6 add 10 is 16, halved is 8, 3 8 to 24, so 240 meters. This area A represents the journey of that is 240 meters. This here is a trapezium now, isn't it? So I don't have to split it up into a triangle and a rectangle. I can do it all in one go. I can see that from 30 to 70 is 40, and from 30 to 100 is 70, and nice and convenient, the height of that okay, is 10. So half of, I'm going to go straight into it now, 40 plus 70 times 10. 40 add 70 is 110, halved is 55 times 10, which is 550 metres. And so the total journey is equal to that, which is, what's that, 790 metres. That describes this one here. So you often get those where they, they slow down and they don't slow down to stop in at the other end, perhaps. Those are the ones that you're going to be doing in the main. On the exam, if they're going to ask you one, it's going to be the velocity time graph. They're going to ask you to sketch and sort of solve problems. I'm going to do a lesson 2A to this, and I'll go through exercise 9B. There's about 8 questions, so I'll do half of them. I'll just do the, the even numbers, say, and you can fill in the gaps. So you might want to do the even numbers with me first, and then fill in the gaps and do the odd numbers. I hope that was clear for you. Just to remind you, we went through distance time graphs. You've seen those at GCSE, even at foundation level, very, very basic, and we're going to concentrate on these, and they describe situations of constant acceleration. And the key point of this was, of course, area under the graph is the distance travelled or displacement. Learn your formula for trapeziums for this, guys. Okay, over and out.